Motion of a pendulum, shown in figure 3, is modeled by this differential equation. Theta is the angle in radians that the pendulum makes with the downward vertical, t seconds after it begins to move. We're asked to show that a particular solution of the differential equation is this, and then we're going to find the general solution. Okay, sounds good. So to show that this is a particular solution, actually all we got to do is sub in and show that the left-hand side is equal to the right-hand side. So if theta is equal to this, then d theta by dt, well, we use the product rule here. So it will be 1 over 12. I'll multiply that back through at the end and then deal with the product rule on this. So I'm going to differentiate t, which is just 1, and times by sine 3t, and add t multiplied by the derivative of sine 3t, which is cos 3t times by 3. So that'll give me 1 over 12 sine 3t plus 1 over 4t cos 3t. Then the second derivative, okay, now I'm going to differentiate sine 3t, so I'll get a quarter cos 3t. Then, okay, I'm going to deal with it all in one go now. I'm not going to factorize that quarter out or anything. So I'll just deal with this as my u, and this is my v. That would have been simpler to start with, to be fair. Right, I'm going to get a quarter cos 3t plus a quarter t times minus 3 sine 3t. Bring this together, we've got a half cos 3t minus 3 quarters t sine 3t. Okay, so therefore, d2 theta by dt squared plus 9 theta is going to equal a half cos 3t minus 3 quarters t sine 3t plus 9 lots of theta, which ends up being 3 quarters t sine 3t. So these cancel out, and we're left with just a half cos 3t, which is what we had here. So the result follows. Therefore, theta, what is it, particular solution is equal to, sometimes that's called, or a particular solution. Yeah, sometimes call it the particular integral. But anyway, it's going to equal, 1 over 12t sine 3t. And let's find the general solution of this. So the general solution, theta, general solution is going to be the complementary function plus the particular integral. And for this one, we're going to be solving d2 theta by dt squared plus 9 theta equals 0. And then the particular integral is the one that deals with that. So what we do is we let theta equal e to the kt. And if you differentiate it twice, you'll get k squared e to the kt, and add that to 9 e to the kt, divide through by e to the kt, and we get what we call the auxiliary equation. K squared plus 9 is going to equal 0. That means k squared is going to equal minus 9, and k is going to equal plus or minus 3i. Then theta ends up being a. Now you could write e to the 3i plus, so a e to the 3i plus b e to the minus 3i, but it's possible to rejig that and get it in terms of real functions, cos and sine instead. Sorry, that is our complementary function. I always like to just explain where that comes from. Just, you would have hopefully have seen it, but let's just imagine for a moment that I'm just going to call it capital C and then say it's e to the 3i plus d e to the minus 3i. Now we can use the Euler's relation and write that as C cos 3t plus I sine 3t. plus d cos minus 3t, but that just is the same thing because cos is an even function, plus I sine minus 3t. Well, that one's an odd function, so it becomes minus I sine 3t. And then you can see we can just collect it up. C plus d times cos 3t plus I c minus d sine 3t. And essentially this here is our A and this here is our B, and they will be real. So that's just showing where that comes from. And then that means kind of running out of space. Let me do it up here. I've got enough space here. So the general solution is actually going to be that A cos 3t plus B sine 3t. Don't forget, we're going to add on our particular integral 1 over 12t sine 3t. Right, now, next part, we're told some initial conditions. I've also written down my general solution again. So initially, that is going to be when t is equal to 0. We're told that theta is equal to pi over 3. And, oh, it's at rest, which means d theta by dt, that's the change in angle with respect to time, is going to equal 0 because it's not moving. And then we're asked to find alpha when t is 10. But first of all, we need to find out what a and b are using these conditions. So I can say that pi over 3 is going to equal a times cos 0, which is just 1, so that's just a. And then the b is just b sine 3t is 0, and 0 when I put in for t into this function here as well. So a is pi over 3. Now let's work out d theta by dt. That's going to become minus 3a, sorry, sine 3t. What am I doing here? Sine 3t plus 3b cos 3t. And then I've got to do the product rule again. I know I did it earlier, so you can look up, but let's just quickly do it. So I'm going to get 1/12 sine 3t, and then got a feeling that actually it's not going to matter. This function is not going to matter, but in any case, let's do it. So then I'm going to get a quarter t cos 3t. Right, so when t is 0, we've got d theta by dt equal to 0. So 0 is going to equal, I get 0 here now. I'm going to get 3b cos 0, and then the rest is 0. So actually b is 0, which means that theta, see, this is what I would now call our particular solution. It's going to be pi over 3 cos 3t, no b, but we've got a 1 over 12t sine 3t. Right, now we're told when t is 10, the angle is alpha, and we're asked to work it out. So when t equals 10, theta is going to be pi over 3 cos 30 plus 10 over 12, which is 5 over 6 sine 30. And just put that in your calculator. It actually gives minus 0.6618. Now it's negative, but we're talking about the angle. So all it's mean is the angle's sort of gone over here. It's the angle is still going to actually be positive. I don't think the sign matters in the mark scheme, but we're going to say that alpha is therefore 0.662. Now, we're told that the true value of alpha is actually 0.62, and we're asked to evaluate the model. So you can either say it's a good model or a bad model. You just got to give some justification. So option 1 is to say that, yeah, 0.662 is roughly equal to 0.62. So model is, well, I said is reasonable. I mean, it's not amazing. Or you could work out the percentage error. So the percentage error is the error, which would be the difference, divided by the true value, then multiplied by 100. This is actually 6.7%. So again, it's all relative, isn't it? I mean, it's not that bad, but I wouldn't say that was a particularly, it depends how accurate you want to be. But if you're 6.7% out with readings, I don't think personally that is like that great. So as long, but you have to just, in this case, you have to basically do this sort of thing. It's not just about the difference, it's all about the percentage error. So model is not reliable or appropriate. Okay, so those are your kind of two different avenues in this question. Finally, last part, we're told that this differential equation, after all, actually models the motion of a pendulum as moving with forced harmonic motion. It's kind of been pushed or something. We're asked to redefine the differential equation so that the motion of the pendulum is actually simple harmonic motion. Okay, simple harmonic motion is actually when your acceleration, which is your d2 theta by dt squared, it's your angular acceleration, is actually proportional to the displacement, but in the opposite direction. So it's when you have it equal to minus like omega squared theta, um, no other terms. So actually, in our case, we just need to make it equal to 0. Make this plus 9 theta equal to 0, because then that will be the case. It will depend on the angle. It's similar to the displacement, and yeah, it'll be negative. So basically, here's our pendulum, when it's over here, it's going to be, it's like the displacement, the angular like amount is positive, and the acceleration is going to be this way. So it's going to be like slowing down, then coming back in and accelerating towards the middle. But as soon as it gets this side, it's going to then change and be accelerating this way because the angle here will be negative. And that is what we need for our simple harmonic motion. I mean, there's lots to read up on it, just a little summary of it, but that is what we're looking for our answer. Well done.